Because tomorrow, because tomorrow's the game that night, and actually just because of the way the lessons fell, I'm going to talk to you about two parts of this lesson, parts of these notes. I'm going to talk to you right now about this idea and this idea. This part we will do tomorrow. And so we'll finish that up tomorrow, and then I'll let you work on that in class. Okay? All right. So this first page. This is understanding what that standard error of the slope means. Okay? It has a real important meaning, and I want you to grasp what that is. Okay. So that and standard deviation of the residuals, what those are and what those do for you. So here we go. Let's start with the standard deviation of the slope. To start this problem out, I want to start with an example. Let's say that we are wanting to take age of Aledo ISD students, and we are wanting to relate that to the weight at those particular ages. Okay. So let's think about this. I'm going to pick 3 students, and I'm going to have them decide how they want to collect data. They're going to collect a representative sample from Aledo ISD. Okay, this is just like hypothetical, so you're just thinking this is going to happen, okay? So Zach is going to go and figure out how to get a representative sample of Aledo ISD. He's going to get 12 students' names. Okay, and then Jacob is going to do that, and Reed is going to do that. So we're going to have 3 people all getting samples of 12 students. No, this is just in theory. Okay, so you get those numbers, and then you make your plot. All right, then if each one of those people computed the least squares regression line, the equation of the line, what would happen? Would Zach's line be the same? The equation of Zach's line be the same as the equation of Jacob's line? So the answer is no. Why would there be some differences between the equation Zach got and the equation that Jacob got? No. You just hush because you are so far out of it, you're not even in the vicinity. So why would there be differences? Because they're different samples, period. Okay? His sample is not the same as his sample, therefore, there's going to be some different subtleties in the equations of those lines. Okay? Now, here's the thing though. If all of you guys did this, should your equations be somewhere in the same vicinity as the others? Yes, if you had a good method of collection. I see where you're going with this, no bias, okay? So if you all got a representative sample, then yes, these should be all in the same vicinity. Okay, but there's going to be a slight bit of difference. Just hold your thought. So here we go. That's what has to happen. That's where this standard deviation of the slope comes into play. I want to know, if your slopes are different, what's a reasonable amount to be different? Or if your slope is really, really different, how do I know if it's way whacked out and you have gotten a poor sample and it's not representative? Okay, so that's what we are going to look at here. So, standard deviation of the slope occurs because we know that the slope of the least squares regression lines are going to vary a little from sample to sample. And so if we gathered a whole bunch of repeated samples, then we would see that the slope is going to be approximate, but not exactly. It's going to be close to what the slope of another sample that we gathered is. Okay. So here I want us to look at this as a picture. I see things much more visually. Okay, so here we go. Let's say that this is Zach's data that he collected. He's graphed it here for Aledo ISD students and their weight. And so I would like for you right now to draw a solid line of your guesstimate for the least squares regression line, okay? So go through that and draw yourself a least squares regression line. Okay, I'm not the best straight looking one, but anyway, so there you go. Okay, so there is my least squares regression line. Now, I want to tell you that the slope that Zach got is 1.5 pounds. So the slope of this line, write that in there, is 1.5 pounds per year. Okay. I also know that the standard deviation of the slope is 0.25. So this is a measure of how much these slopes can vary. If I get a slope that is 1 standard deviation up, what would it be? I get a slope that is 1 standard deviation greater than Zach's, it would be 1.75. Very good. Let's kind of draw that in there. It's not necessarily going to have the same y-intercept. It may, but it may not. It probably is going to be something more like this. You're going to cross somewhere, his line, and you're going to end up with something like this. Let's say that the slope of, this one is Jacob's line, is 1 standard deviation up. So he has 1.5 plus 1 standard deviation. So his slope is 1.75 people per year. So I would not think something wacky is going on if he got a slope of 1.75. I'm like, oh yeah, that's reasonable. I mean, it's just a little varied. But if somebody had a slope of 5, would I be alarmed by that? Yeah, because 5 is a whole bunch of standard deviations different. That's why you need this. It gives you a reference of what size is reasonable and what variation can happen. Let's just kind of figure out an acceptable range. We know outside of 2 standard deviations it's going to be what? An outlier. I'm sorry. Outside of 2 standard deviations it's going to be outlier stuff, right? Okay. So what would be 2 standard deviations up? A slope. What would be the slope of 2 standard deviations up? It would be 2. Very good. So 1.5 plus 2 standard deviations gives me a slope of 2. Okay, so that would be the most extreme slope that I would expect to happen in any of our samples. If somebody got a different a slope different than 2, then I would start thinking something is happening and something weird is going on. Let's find the lower bound. If somebody did 2 standard deviations down, that would be 1 because it's 1.5 minus 2 standard deviations. So that's how I get a lower bound slope of 1. So in this instance, in this context, if somebody got a slope outside of the range from 1 to 2, then I would have to reanalyze what's going on and think something's happening. Okay? So that's what standard deviation of the slope does for you. It gives you this amount to know if it's messed up or not. Things are messed up. Okay. Likewise, standard deviation of residuals. Okay, so let's kind of go back to definition first. What's the residual? What's a residual? It's that, okay, it's that distance from the actual to the predicted. Okay, so it's that distance from actual to predicted. Okay. What about standard deviation? Again, what's our concept of standard deviation? That's what is the definition of standard deviation? Close. Yeah, the deviation from the mean. It's the average deviation, the distance from the mean. Okay, so that's what's happening with this residual standard deviation. It is going to be an average distance that the actual values are away from the predicted values, okay? So on this picture here, I'm going to draw this line. This is the same data. It's the residual plot of the data up above. It's still the age of the Aledo ISD, and then we're talking about the residuals of their weights. So this line I just drew, what does that represent? Okay, the least squares regression line. So these are the predicted values. Okay, good. So these are the predicted values, and then I can see how the actuals related to that, whether they were above it or below it and that kind of stuff. So guess what? I am told here that on this residual plot, the standard deviation is 3 pounds. So, let's look at where that would be on this graph. Okay, so here's a residual of 0. 3 pounds up, of course, would be about right here. Okay, so draw a dotted line there. And then 3 pounds down is going to be about right here. Okay. So these are the data points that are within 1 standard deviation of what was predicted. Okay. So these are the actual points that were within 1 standard deviation. So they're good. They're reasonable. They're reasonably placed around the predicted line. Think of the normal model. What percent of points should fall within 1 standard deviation of the predicted? Good, 68%. Let's think about that for a second. If I look at this, there are 12 actual data points here, and if I counted, I've got 8 of them within 1 standard deviation. Well, guess what that comes out to be? 6, 6, 6, 6, 6, 6, repeating, so rounds to 67%. Okay, boom. So we're good. We're seeing a good relationship there. Let's do 2 standard deviations out. Okay, let's draw 2 standard deviations out. Here we go. Where's that going to be? 6 pounds above predicted. So 6 pounds above predicted is 2 standard deviations up. 6 pounds below predicted. I think that actually takes you to this bottom axis here. So guess what? All but 1 are contained, and so that's 11 out of 12. How many would I expect? What percent of data would I expect to fall in there? 95%. If you do this, it's actually 92%. So I'm pretty close to 95. So yay, that worked out well. Okay, we're not done. I don't know, what time did you get out of here? It's like Bell about to ring. Dang. Okay, sorry. Then I guess in this class we'll have to talk about the we'll have to talk about the other 2 concepts tomorrow. Okay.